on my presentation, creating Python code to determine the best orbital transfer in a given scenario. My name is Alexander Castronovo. I'm a 14-year-old attending a high school offered by Stanford University. I'm here today with the Wolfpack CubeSat development team. The leader of the team is Mr. Kevin Simmons, and I became interested in orbital mechanics thanks to a lesson that Mr. Simmons taught on calculating orbital transfers. Frame things, let's suppose that you are a mission planner. It's 9 a.m. on a Monday morning, and you've just been assigned a new task to move a satellite from a low Earth orbit, parking orbit, to a lunar orbit. You have been informed of one constraint for this mission, and that is that the satellite needs to arrive in less than 2 weeks due to project management concerns. How are you going to do it? Well, it's likely you're going to use something called an orbital transfer. Orbital transfers allow a satellite to move from one orbit to another. There are many different types of orbital transfers. All of the orbital transfers between two circular orbits have at least 2 engine burns and 1 transfer ellipse. An orbital transfer works by, at these engine burns, giving energy, applying specific mechanical energy to an orbit to increase the orbit altitude. This Python program that my team and I created considers 3 different types of orbital transfers: the Hohmann transfer, the faster than Hohmann transfer, and the bielliptic transfer from left to right on the slide. Starting off with the Hohmann transfer, it has 2 burns and 1 transfer ellipse. So the first burn adds specific mechanical energy and puts the rocket on this blue transfer ellipse. The apogee of this transfer ellipse touches the final orbit. So once the rocket reaches the apogee, it burns 1 final time to the final orbit. Here, the faster than Hohmann transfer is similar to the Hohmann transfer in that it has 2 burns and 1 transfer ellipse, except the transfer ellipse extends past the target orbit, giving more energy to the transfer ellipse, making the transfer shorter overall at the expense of more fuel. And here is the bielliptic transfer. This is the most interesting transfer and is supposed to save fuel at the expense of time of flight. So this works by the first burn puts the rocket on the blue trajectory. At the apogee of this blue trajectory, it burns 1 more time onto the red trajectory, and then finally it burns 1 final time to put itself in the target orbit. This third burn is interesting because it takes away energy from the orbit instead of adding energy. It takes away energy instead of adding energy, which is called a retrograde burn. So now that we know which transfers the Python program considers, how do we know which one to use? We have to take into consideration that fuel efficiency is traded for time of flight, and we have to find the best balance from the mission constraints, which is the fuel on board the spacecraft and the mission time frame. In our case, fuel is not an issue, but our mission time frame is 2 weeks. On the left here, you can see the user interface for the Python program that allows you to easily calculate these orbital transfers. So you have 4 input boxes, then 3 buttons, one for each of the transfers, and then an output. So looking closer at the inputs, we have gravitational parameter in kilometers cubed per second squared, initial semi-major axis, final semi-major axis, and transfer radius are all in kilometers. And the transfer radius is the distance from the center of mass of the orbiting body to the highest point of the transfer ellipse. The Python programming language here is used over others like C++ or Java because it's a common intuitive programming language that allows students and professionals to easily read and modify the source code even with minimal programming experience. And also out of the box, Python allows numbers to go over the 64-bit integer limit, which may be useful in some cases. I'd also like to point out here that this project is open source, so if you have any experience with programming or orbital mechanics, I encourage you to contribute to this project. I'll have my email at the end, and you can email me the link to the source code. Looking at the raw results here, we can see that the delta V, I use delta V as a proxy for fuel. Delta V is change in velocity, and TOF is abbreviated for time of flight. Looking at a much prettier representation of this data, we can see that the bi-elliptic transfer, unsurprisingly, uses the least amount of fuel with 3.8 kilometers per second. The Hohmann transfer uses a little bit more fuel, 3.9 kilometers per second, and the faster than Hohmann transfer uses the most at 4.1. What I found surprising, however, is that while the bi-elliptic transfer saves a minuscule amount of fuel, it takes nearly 8 times longer compared to the Hohmann transfer. I thought this was a strange result, so I modified the program to produce 10,000 different data points with different transfer radii, and what I found was a graph of diminishing returns. So on the y-axis here, we have the delta V saved relative to the Hohmann transfer in kilometers per second, and on the x-axis we have the time of flight in days. We can see that even the shortest transfer, which saves no fuel, still takes about 18 or 19 days, which is out of our mission time frame. Because of this, and because the faster than Hohmann transfer is not needed in this scenario, the recommended transfer in this scenario is the Hohmann transfer. I found this project engaging to me because it connects both of my interests of orbital mechanics and computer programming. And between orbital mechanics and computer programming, Python is also important in the classroom because it allows students to connect what they learned in science and mathematics to the real world using code. Thank you. Does anyone have any questions?
Thank you very much.